First example, the use of these Taylor and Maclaurin series then. Let's explore this function, the function e to the x. We've already differentiated this one in the drill, and we're going to explore the function so that we know that because we know that it exists at 0, we're going to let a equal 0. So we've got this to explore. So the first thing to do, if a equals 0, is we're actually going to use Maclaurin series. And if we look at Maclaurin series, which is down here, we can see that to write this function as a power series, we need the values of the function at 0, the values of first differential, the second differential, and so on, to find out what these are. So what we do is, to start off with, we find out what the first differential is, what the second differential is, and so on. So we can almost set out a table. We write down our function, it's e to the x. So then for the constant, we want to know what is c0. We want to know what the value of the function at 0 is. Then we differentiate the function. We differentiate e to the x. Well, remember that is actually the same, e to the x. So the value of the first differential of x is e to the x. And then again we want what's the value of the first differential at 0. Differentiate again to get the second differential. What's the value of the second differential at 0? Differentiate again for the third differential. What's the value of the third differential at 0? And so on. Usually when you start to do this, you see a pattern emerge. So after actually about 4 or 5 different differentials maybe, you can see a pattern, so you don't need to carry on. Not always, but often. So what do we do now? Okay, the value of the function is e to the x. So that f0 is just 1, anything to the power 0 is 1. The value of the first differential at 0 is also 1, the second differential is 1. So in other words, the pattern is that it doesn't matter what the differential is, the value of the differential at 0 is always 1. So if we now apply that to the Maclaurin series, what we're saying is that this, the nth differential at 0, is always 1. So what we have is effectively that just the function is the sum of x to the n over n factorial, where n equals any value from 0 to infinity. And writing this fully out, when n equals 0, anything to the power 0 is 1, so the first term is 1. When n equals 1, we have just x. When n equals 2, we've got x squared over 2 factorial, and so on. Just pause and check that you see that this, n equals 0, 1, 2, 3, 4 up to infinity, will give you this up to infinity. That's our power series. Remember, we need this series to converge for us to be able to say that this power series can be used to represent this function. What we can do, one way to this is to do a ratio test, which means you take a function, you take a term rather, and divide it by the previous term and see whether or not it gradually gets smaller and smaller. And if you remember when we did our drill, the criteria was that the value of x needs to be less than 1. So what we're after is, in the limit, as n tends towards infinity, if the ratio of the top one term divided by the previous term is less than 1, that must mean if it's less than 1, it's getting smaller. If the division of a term divided by the previous term is less than 1, it must be getting smaller. So if we take this particular one, if I divide a term, let's take that n equal n plus 1, and divide it by x to the n over n factorial, can you see that that's a term divided by the previous term? Well, if we think about that, if we divide one fraction by another, this fraction can be inverted and multiplied. So we can write x to the n plus 1 over n plus 1 factorial multiplied by n factorial over x to the n. Now we can do some cancelling because we've got n lots of x underneath, but n plus 1 lots of x on top, so that just leaves us one value of x on top. Similarly, n factorial is all the numbers from n down to 1 multiplied together. N plus 1 factorial is all the numbers from n plus 1 down to 1 multiplied together. So I can cancel all the n's, and all I'm left with is n plus 1. So I end up with x over n plus 1. In the limit, as n tends towards infinity, if you look at this term, as n tends towards infinity, then the number underneath in this fraction here is going to get bigger and bigger, which means that the answer tends towards 0. So in the limit, as n tends towards infinity, 1 over n plus 1 tends towards 0. So it actually doesn't matter what x is, the whole thing is going to tend towards 0. In other words, it's less than 1. So for this particular power series, it doesn't matter what x is, the series will converge, and so that means that this power series can be used to represent the function e to the x for any value of x. If we put this into autograph, we can see that the power series does actually start to look more and more like the e to the x function. So if I put in the function y equals 1, shift this over here, y equals 1, which is this here, you can see that, well, actually they do cross when x equals 0. If I now add the next term, which is 1 plus x, then we can see the line starts to follow the e to the x curve around x equals 0, which is where we're exploring the function, remember, when a equals 0. Now when I add x squared, the next term, over 2 factorial, or just 2, we get this, and you can see it follows the e to the x curve a bit more either side of the value of x equals 0, which is where we're considering it. So for values of x greater than or less than 0, we can use this power function to represent e to the x so long as we're close to 0. I add the next term, e to the x cubed, so that's plus x cubed over 3 factorial. I can use the exclamation mark here to represent 3 factorial. And now you can see that even more closely it follows. So from this we can see that we can use the power series to represent e to the x at x equals 0, more and more away from 0, the point we're considering, as we add more terms. So if we add many terms, we can actually use e to the x to represent the function over a wide range of values for x. And actually, your calculator, if you type in what is e to the power 3, for example, how does it work it out? It actually uses the power series for many values of n for being a large value, to give you that power. So power series is the way that the calculator calculates the functions on the calculator. It uses the power series. Okay, I'll stop that there and then perhaps have a look at another example.